Welcome back to CyberTechHaus. I am glad you are joining us as we move into Module 3, Cryptography Part 1. In this module, we will build on the basics we covered earlier and explore some of the most important ideas in cybersecurity. Think of these concepts as the building blocks of security. They are essential to understanding how and why we protect data, networks, and systems. By the end of this module, you will have a solid grasp of these core ideas, giving you a strong foundation as we continue into more advanced topics. So let's dive in and start mastering the fundamentals of cybersecurity. Module 3, Cryptography, Part 1, Understanding Encryption. Cryptography is one of the most essential tools in information security. It keeps sensitive data safe from unauthorized access and plays a crucial role in many of the security features we rely on every day. But what exactly is cryptography? Let's break it down. Number one, definition of cryptography. Cryptography is using mathematical formulas or algorithms to transform readable information into something that no one can understand. Imagine you have a message that says hello. Using cryptography, you can scramble that message into a form only the right person who has the key can unscramble. Number two, encryption and decryption. When we use cryptography to scramble data, that is called encryption. It takes information that is easy to understand and converts it into unreadable format. Only someone who is authorized and has the right key can convert that data back to its original readable form. This process is called decryption. Now, you might be wondering, why does cryptography matter so much? Well, without cryptography, sensitive information could easily fall into the wrong hands. Encryption keeps data secure, whether personal information, financial data, or business secrets. Cryptography underpins many security systems we use, such as secure websites, virtual private networks, VPNs, and data protection in messaging applications. In short, cryptography is about protecting information by making sure only the right people can read it. It's one of the foundations of cybersecurity, helping us safeguard data and maintain privacy in a digital world. Cryptography, understanding encryption. All right, students, let's unlock the secrets of cryptography. Imagine it as the art of secret codes, like something out of the spy movie. But it's not just for spies anymore. We use it daily to protect our online information. What exactly is cryptography? Imagine you want to send a secret message, and that message is hold my beer to your friend, but you don't want anyone else to read it. Cryptography is like using a special code to scramble your message so only your friend with a secret decoder ring can read it. We call the original hold my beer message plain text. That is what you want to keep secret. Cryptography turns it into a cipher text. It's the jumbled mess that no one can understand without the key. Encryption and decryption. Encryption is like putting your message in a special box and locking it with a key. Now it is safe from prying eyes. Decryption is like using the key to unlock the box and reveal the original message. Together, encryption and decryption make sure your message stays secret and only the right people can read it. Algorithms, the recipe for encryption. An algorithm is like a recipe with step-by-step instructions. In cryptography, an algorithm tells you exactly how to scramble the message. Think of it as a cake recipe. You follow the steps to mix the ingredients and bake the cake. Cryptographic algorithms are similar, but they use complex mathematics instead of flour and sugar to scramble the data. Now, I want you to think of something, and I'm going to ask you a question. Imagine you are writing a secret note to your best friend. How would you use cryptography to keep it secret from your nosy friend or even your little brother? You would be correct to think that you could use a simple code like shifting each alphabet letter by one position. That is a basic form of encryption. However, we use much stronger algorithms to protect critical secrets. The key takeaway here is cryptography is all about protecting information by scrambling it into secret code. It's like having a secret language that only you and your intended recipients can understand. And that's how we keep our data safe in the digital world. Symmetric versus asymmetric encryption. Okay, students, today we're going to talk about two main types of encryption, symmetric and asymmetric. Think of them as two different ways to send a secret message. Symmetric encryption. This is like having a secret code that you share with your friend. Let's say you both know the word banana is the key. You can use this key to scramble your messages so only someone who knows the key can read them. It's simple and fast, like a shared password. But here is the problem. What if you want to send secret messages to more people? You will need a different secret code for each person. Imagine if everyone in the class needed a different secret code to talk to each other. That would be a lot of codes to remember. Asymmetric encryption. This solves the problem at hand by using two keys instead of one. It's like having a mailbox with two slots, one for sending mail and one for receiving mail. Everyone has their own mailbox with their name on it. The sending slot is like their public key. Anyone can use it to send the message. But the receiving slot is like their private key. Only they have the key to open it and read the messages. So if Bob wants to send Alice secret message, he puts it in the sending slot of Alice's mailbox, her public key. Only Alice can only open her mailbox with her private key and read the message. The cool thing is that everyone only needs one mailbox with two slots. This makes it much easier to manage all those secret messages, even in a large group. In a nutshell, symmetric encryption is like a shared secret code, while asymmetric encryption is like mailboxes with separate slots for sending and receiving. Both are important for keeping our information secure in different ways. Cryptography has several key goals. Now, cryptography has a few main goals: confidentiality, integrity, authentication, non-repudiation, and obfuscation. These are the superheroes with different superpowers. Let's check them out. Confidentiality. This is like making sure only the people with the right key can open a secret message. Think of it as a locked treasure chest. Only those with the key can see the treasure inside. We use this to protect data when it's stored on a computer, sent over the internet, or even when it's being used. Integrity. This is like making sure nobody messes with your message while it is being sent. Imagine someone intercepting your message and changing the meeting place. Integrity ensures the message arrives exactly as you sent it. Authentication. This is like making sure the person you're talking to is really who they say they are. Think of it as a secret handshake or a password that verifies their identity. Non-repudiation. This is like having a signed contract. It proves that someone sent a specific message and they cannot deny it later. Think of it as a digital signature. It's like a unique fingerprint that confirms the sender. Then, obfuscation. This is like hiding information in plain sight. Imagine writing a secret message in invisible ink. It looks like a blank page, but the message is there if you know how to reveal it. We use this to protect sensitive information like medical records or financial data. So, there you have it, the 5 superpowers of cryptography. They work together to protect our information and keep our communication secure in the digital world. Choosing encryption algorithms. Selecting the appropriate encryption algorithm is crucial for safeguarding sensitive information. Our primary consideration is choosing between symmetric and asymmetric encryption. As we discussed, symmetric encryption utilizes a single secret key for encryption and decryption, offering speed and efficiency but necessitating secure key distribution. In contrast, asymmetric encryption employs a pair of keys, public and private, enhancing security by eliminating key distribution challenges, though it operates more slowly. The critical takeaway is security versus performance. Stronger encryption needs more processing power, so balancing security and speed is essential. Another vital factor is the critical length, which determines the strength of the encryption. Longer keys provide greater security, but require more computational resources. For instance, a 256-bit key offers robust protection, but may impact performance compared to shorter keys. Balancing security needs with system capabilities is essential when selecting key length. The critical takeaway is key length. Longer keys provide more security but may slow down processes. Choose an appropriate key length based on the data's sensitivity. It's also essential to choose algorithms that are extensively vetted and endorsed by the cybersecurity community. Widely accepted standards like the Advanced Encryption Standard, or AES, for symmetric encryption and RSA for asymmetric encryption are recommended due to their proven reliability and security. Implementing these well-established algorithms helps ensure the protection of sensitive data. Again, the critical takeaway is to use proven algorithms and to avoid creating your own. Use reliable, well-tested algorithms instead. Cryptographic life cycle. Cryptography isn't static, it evolves over time. Organizations follow a life cycle to keep encryption secure. Cryptographic algorithms and the keys to protect information are essential to any security program. Cybersecurity professionals must understand the cryptographic life cycle to effectively manage these algorithms, selection, maintenance, and eventual decommissioning as security needs evolve and threats change over time. Over time, cryptographic algorithms can become insecure. This happens because researchers discover flaws in how they are implemented or because the keys they use become vulnerable to attacks such as brute force attacks. For this reason, adopting a life cycle approach to cryptography is necessary, ensuring that algorithms are phased out when they are no longer secure. The National Institute of Standards and Technology NIST 857 Part 1, Revision 5, titled Recommendation for Key Management Part 1 Journal, outlines a 5-stage cryptographic life cycle that organizations should follow when using cryptography. Let's go through them quickly. Number 1, initiation. In this first phase, the organization identifies the need for a new cryptographic system and gathers requirements based on their specific security needs. This includes setting clear goals for confidentiality, integrity, and availability based on the sensitivity of the information being protected. For example, NIST suggests that the objectives might consist of protecting key integrity, ensuring authentication and non-repudiation, maintaining 99.5% availability, and using digital signatures to verify both the sender's identity and the message's integrity. Number 2, development or acquisition. In phase 2, the organization either develops or more commonly acquires the cryptographic system. This means finding the right mix of software, hardware, and algorithms that meet the security objectives defined during the initiation phase. Stage 3, implementation and assessment. In phase 3, the organization configures the cryptographic system and assesses whether it adequately meets the security needs identified earlier. This step is crucial to ensure the system performs as expected and provides the necessary protections. Stage number 4, operations and maintenance. Once the system is in use, it moves into phase 4. During this phase, the organization continuously monitors and maintains the cryptographic system to ensure it functions securely. Regular updates and monitoring are essential to keep it practical. Phase 5, disposal or sunset. The final phase occurs when the cryptographic system is no longer viable for long-term use. In the disposal or sunset phase, the organization stops using the system and ensures that sensitive materials like cryptographic keys are either securely destroyed or archived. In summary, the cryptographic life cycle helps organizations manage cryptographic systems over time, from initial planning to eventual retirement. This process ensures that cryptographic protections remain strong and adaptable as security needs change. Identification, removing or anonymizing identifiable information from data to protect privacy. Data de-identification in cybersecurity is a process used to protect personal information. Here is a simple way to understand it. Imagine you have a list of people with sensitive information, like names, social security numbers, and addresses. De-identification means removing or altering the parts of that data that could directly identify someone, so that even if someone sees the information, they can't tell who it is about. In cybersecurity, this means taking out obvious identifiers like names or ID numbers, and sometimes even more subtle details. So it is much harder to connect the data back to an individual. For example, you might replace names with codes or remove exact birth dates. The goal is to keep the data useful for analysis or research, but without exposing personal details that would compromise someone's privacy. Let's break down how masking and tokenization help with the data de-identification in cybersecurity, which is all about removing or hiding personal details so the data can't be traced back to specific individuals. Masking. Imagine you have a customer's sensitive information, like their social security number 123456789. With masking, you cover up parts of this information, showing only some digits. In this example, we're going to show only the last 4 digits and mask the other part with X's. This way, people can still recognize that it is a social security number and see more partial details, but they cannot see enough to identify the person. In cybersecurity, masking is a common method for de-identification when data is shared or displayed, especially when full details aren't necessary. For example, employees may need to confirm parts of someone's social security number without viewing the entire number. Masking keeps personal information protected while allowing access to some limited details. Tokenization. Now, let's look at tokenization. Instead of partially hiding the real information, tokenization replaces it with a random code. For instance, turning the social security number 123456789 into ABCD 9876. This token has no connection to the original number, and it is meaningless outside the secure system where it is stored. The real social security number is kept separately, securely stored away, and only linked to the token within the system. In cybersecurity, tokenization is especially useful for de-identifying data in cases where sensitive information needs to be processed or transferred securely. For example, if a company needs to work with customer data but doesn't want to expose the actual social security numbers, it can use tokens instead. All right, putting it together, both masking and tokenization are tools for de-identification. Masking hides part of the data, making it harder to identify individuals by showing only partial information. Tokenization replaces the real data with a random code, making it impossible to trace back to the original data without access to the secure system. Together, these techniques allow organizations to use or display data without revealing personal information, helping protect individuals' privacy. Data obfuscation. Data obfuscation in cybersecurity is a way of hiding sensitive information by transforming it so it's hard to understand or recognize. Let's break it down simply. Imagine you have a list of customer phone numbers or social security numbers you don't want unauthorized people to see. With obfuscation, you make that data unreadable or unrecognizable So even if someone accesses it, they can't quickly tell what it is. One way to do this is to replace the actual data with the random characters or codes. For example, turning a phone number like 123-456-7890 into something like XXX7890. Another way is to use hashing or encryption to scramble the data entirely so it looks like random characters to anyone without the right access. Data obfuscation aims to keep the original information safe while allowing people to work with the data in its scrambled form. It's like creating a puzzle. The data is there, but without the key or solution, it's just a bunch of random pieces. This technique helps protect sensitive information, even if it is accidentally shared or exposed. One can transform data so it's unreadable using techniques that include but not limited to hashing. Hashing converts data to a fixed code but cannot be reversed. Sorting. Sorting adds a unique value to data before hashing for extra security. Tokenization. Tokenization replaces sensitive data with unique identifiers. Masking. Masking hides sensitive data with placeholder values, for example, the XXX that we have mentioned before. Let's break down these terms using simple explanations. Let's start with hashing. Hashing is like creating a digital fingerprint of data. Imagine you have a password and you run it through a special formula called a hash function that turns it into a fixed scrambled code. This code, called a hash, always looks the same for the same input, but it can't be reversed back to the original password, for example. So, if someone sees the hash, they can't figure out the password. In cybersecurity, hashing is used to store sensitive information like passwords safely. Sorting. Sorting is like adding a secret ingredient to your hashed data. Let's say two people have the same password. Without any extra steps, their hashes would look identical, which isn't a very secure way of keeping passwords. A sort is a random piece of information added to each password before it is hashed. So even if two people have the same password, their hashes will look different. This makes it much harder for attackers to guess passwords, even if they manage to see the hashes. Tokenization. Tokenization is like giving data a placeholder or a substitute. Imagine you're protecting credit card numbers. Instead of storing the card number, replace it with a random token like 12345678 XXXXXXX. This token is meaningless if someone sees it because the original data is stored somewhere safe and separate. In cybersecurity, tokenization is often used for sensitive data in systems where it's important to keep information secure, like in payment processing. Masking. Masking is like covering up parts of data so only part of it is visible. Think of it like showing only the last 4 digits of a phone number or a social security number. In cybersecurity, data masking hides parts of sensitive information, so people who see the data can still use it for things like verifying identity. but they don't see the full sensitive information. This protects privacy while still allowing some useful access to the data. Each of these techniques, hashing, sorting, tokenization, and masking, helps keep data safe by making it harder for unauthorized people to access or misuse sensitive information. In summary, cryptography is a powerful tool in cybersecurity that keeps data secure through encryption, decryption, and careful management. By understanding these concepts, you are building a solid foundation for data protection. Dear students, coming up next is Module 4, Cryptography Part 2. In this module, we'll build on the basics we have covered and dive into some more cryptography. We will continue to look at symmetric cryptography. I want to thank you for watching and see you in Module 4.